Okay, questions? You are preparing for the exam and no? You are already preparing for the exam. Any questions for the exam?
Questions, but maybe we can talk about it after the class.
We can also use the class hour.
Okay. Actually, I have a problem with the calculation of volume of the phase space.
Do you have a particular problem? Or shall we do, for example, the free particle?
Okay.
It's a non-relativistic free particle. Now, if you look at the microcanonical ensemble, so if you remember, we had defined this function omega e, which was the number of particles that have energy E. And then we said that, okay, this number, at least classically speaking, this number is not really finite because every point in phase space is corresponding, not the particles or the microstates. So we have the condition is that we have free particles, so their energy is given by the sum of their kinetic energies, which can be written as p squared momentum of the ith particle divided by 2m summed over all particles. This should be equal to E. Now, how many vectors pi? So we are looking for the number of the sets pi such that they satisfy this condition. That number is infinite in classical physics. But still the number of states you can you can convince yourself that it should be proportional to the area, let's call it, of the hypersurface. That is defined by that condition. Essentially, you can say that the number of points is proportional to this hyper area. Well, it's basically some kind of a volume. So what we do is, rather than calculating this directly, we define some other quantity which turns out to be easier to evaluate, this gamma E. Remember, omega E is the number of particles. Gamma E, number of states that have energy equal to E. So this is, let's say, the volume of the phase space that satisfies the condition. This is less than or equal to E. Because if you know the volume, then you can define the omega E, the area that is basically the derivative of gamma E by the energy E. Now, during the lectures, we had slightly different approach. We said that, okay, we are saying that the energy has to be definitely E, but that's not realistic. So, no matter how you isolate your system, there will be some uncertainty in the energy of the system. So, in the lecture, we had also said that omega of E is gamma of E plus delta E over 2 minus gamma of E minus delta E over 2. This is basically the number of states that have energy within that range. And that is equal to derivative of gamma of E with respect to E times the delta E. No, sorry, this is omega E is the number, not the area. This is the area of in phase space. But I mean, we will show that this, whether you use this definition of omega or this definition of omega doesn't really make much of a difference. And so then the question is, what is gamma E? The volume. Let me put it proportional to not equal to. What is the volume? Now, how do you calculate the volume of an object? Well, the volume is the volume integral. Well, we have a 3n momenta and 3n coordinates. The volume integral of 1. And the domain is given by the Qi is inside our spatial volume, the volume of my system, and pi squared over 2 should be less than or equal to, there's some less than or equal to E. This is the volume. Now the volume integral is kind of trivial since they are not interacting. The Q integrals are independent of each other. There is no Q in this condition also. So we can just say that this gamma of E is V to the power n times the integral of the 3n of P, subject to the condition, this one. Now, of course, this is nothing but, if you look at that expression, that is nothing but the volume of a sphere. So we just go, instead of using the Cartesian coordinates, we can use the spherical coordinates. And in spherical coordinates, this integral would be just the integral of the radial coordinate, in which case it will be p, let's say p to the power 3n, d minus 1, dp, and then the integral over angles. And the condition is now p should be less than or equal to square root of 2me. Now here I had defined the p to be pi squared sum to the power 1/2. This is the 3n dimensional radial coordinate. So gamma of E is then v to the power n, p to the power 3n over 3n times the integral from p from 0 to p is equal to square root of 2me times, of course, there is the angular integral, which becomes v times 2me to the power 3/2 to the power n divided by 3n d omega 3n. Now the technical problem that's left is to evaluate that angular integral. Now the easiest way to evaluate that angular integral would be try to relate it to some other integral that we already know. Let's consider this case. E to the power minus p squared d 3n p. Okay, we can already evaluate this one. If you like, let's just put if alpha, the coordinate alpha over there so that the units will be all fine. Now, on one hand, this is nothing but the integral of e to the power minus alpha p1 squared plus p2 squared plus p3n squared. There are 3n coordinates of dp1, dp2 dp 3n. Well, this is just 3n Gaussian integrals. All of those Gaussian integrals will just give me pi over alpha square root. So there are 3n of them, 3n over 2. On one hand, that integral is equal to pi over alpha to the 3n over 2. Now, on the other hand, I can just do the same trick, go to the spherical coordinates to evaluate that integral. E to the power minus alpha p squared e to the power 3n p. This is equal to e to the power minus alpha p squared p to the 3n minus 1 dp times d omega 3n. But these two should be equal, because they are the result of the same integral. So that angular integral is just pi over alpha to the power 3n over 2 multiplied with p to the power 3n minus 1 e to the power minus alpha p squared dp to the power minus 1. Now, to evaluate an integral, let me first make a change of variable. Of course, here I'm integrating over all p. I'm not restricting it in any way. So the p goes from 0 to infinity. You see, in the previous expression that I'm looking for, the p is restricted to an upper value. But that's not really relevant. What I'm interested in is the integral of the angles. Now, first let me make a change of variable. Let me call alpha p squared as my x. So p is x over alpha, square root of x over alpha to the power 1/2. dp is the x over 2 square root of x, 1 over alpha to the power 1/2. So the integral over all the angular coordinates is pi over alpha to the power 3n over 2. Integral, now we have x to the power 3n minus 1 over 2, e to the power minus x, dx over 2 square root of x, and 1 over alpha to the power 3n over 2. To the power minus 1. Now this alpha basically cancels this one. That should be the case because the angular integral doesn't depend on alpha. So if alpha didn't cancel, we would have known that we have made a mistake somewhere. So what remains? This is pi to the power 3n over 2 dx from 0 to infinity, e to the power 3n over 2 minus 1, e to the power minus x times dx over 2 to the power minus 1. That integral is nothing but the gamma function. So this is divided by gamma of 3n over 2 times 2. Now we know what gamma is. Well, it's the solid angle. Let's go up. There's this factor. Times the angle, the integrals over the angle. This is pi to the power 3m over 2 divided by gamma 3n over 2, and here we have 3n over 2. Now, of course, before in the lecture we said that okay, there is this. This is the volume. If we want to count the number of states, we should divide this by some quantity omega 0, which classically there is no justification. But in quantum mechanics gives us the justification what that omega 0 should be, and omega 0 just turned out to be 2 pi h bar to the power 3n.
So the n is the dimension of the phase space. So 3n.
3n is the dimensions of the half of the phase space. You see, the phase space has the coordinates and momentum. So the dimension of the phase space is 6n dimensional. It has 3n dimensional coordinates and 3n dimensions of momentum.
If we had, instead of n particles in 3 dimensions, if we had 3n particles in 1 dimension, I asked this before, but I have to ask again. So the difference in the calculation would be...
in this case, nothing. Nothing would have changed. 3m particles in 1 dimension or particles in 3 dimensions. But in the homework question, the difference was what is the energy? You see, if you look at the energy expression, so this expression can be written as the n, sum of n terms, each of which is the square of a vector, or it can also be written as sum of 3n numbers, each of which is the square of a number. But if it was not p squared, but let's say the magnitude, then it would have been different. In one, for example, if E was p over 2m pi, then it wouldn't be the case, because this in 3 dimensions, this is just square root of pi x squared plus pi y squared plus pi z squared divided by 2m in for n particles. In 3D, but it will be just for 3n particles in 1D. There is no square roots, etc. It's just a sum of squares. Oh, sorry, not the squares. Sum of the numbers. Sum of some numbers. So gamma E will be just the area defined by a plane, and this defines a plane. Whereas this expression is a very complicated surface. The sum of square roots of the sum of squares. So basically the difference between these two cases, if there is any difference, it is due to the expression of the energy. Whether the expression of the energy is different or the same for 3n particles in 1D or n particles in 3D.
Can we go up more? this case, the expression of energy is. So it didn't change. It didn't change anything. The expression of energy.
Why?
In this free case.
Well, for example, you see, where did we use the expression of the energy? Basically here. You see, the volume is specified by the expression of the energy. And since the energy depends on the sum of squares of numbers, sum of squares of the coordinates, the volume is specified by sum of the squares of coordinates, the surface is basically a sphere. Since it's a sphere, we could separate the radial integral from the angular integral. Because in whichever direction you go, for a sphere, the radial direction, radial coordinate goes from 0 to some upper value which is independent of the angles. If this was not the case, for example, if it wasn't a sphere but some other shape, the upper limit of the p integral would have depended on the angles. In which direction are you going along the radial direction? You see, for example, let's just take a simple case where we are trying to find the volume of, I don't know, cube, or in 2 dimensions, let's say. You have let's say, a square. If you use the radial integrals over here, you see the radial coordinate at this point, in this direction, the horizontal direction, starts from 0 up to, let's say, A. But if you go along this direction, the radial coordinate goes up to B, which depends on the angle. So basically we are using the explicit forms of the energy in this step. If the dependence of energy on the momenta is not given by the sum of the squares of the momenta, that step we cannot do. You see, the separation of the integrals we cannot do.
But wouldn't we call that a sphere in the lower dimensions? Could it be called that a sphere in lower dimensions?
You see, let's get this example over here. This is not a sphere in 2 dimensions, or in whichever dimension you like.
But the 3n particles in 1 dimension case, well, I wouldn't express with a square actually. I would say it's a sphere in 1 dimension. Couldn't I do that?
You see, let's look at the 2-dimensional case. Okay, for simplicity. This case. Let me just remove this M also. Let me just put an off. So basically here we don't have a summation. So we are looking at the volume alpha p less than E. As you said, this is a circle. Okay, so gamma of E d squared p such that p is less than E. This is p is less than E over alpha. and this is pi times E over alpha squared. Okay. Now let's look at this case. So basically the condition we have is P1 plus P2. We have two particles. This should be less than or equal to E over alpha. This is P1, this is P2. This surface, this volume is actually this volume. So this point is E over alpha, minus E over alpha, minus E over alpha. Here on the other hand, in this case, well, there's no px and py. It is a sphere. This point is E over alpha. Minus E over alpha. This is minus E over alpha. This is E over alpha. This is basically the main difference. Now, if you go to higher than 2 dimensions, the n particle case would have a much more complicated surface, because here, since we have one particle, it is still the surface, the volume is determined by the squares of the coordinates. If we have two particles, it will be determined by the square root of the sum squares, the sum of the square roots of the sum of the squares of the various coordinates of each particle. So the area, the volume will not even be a sphere. Nevertheless, in the 1D case, it will still be determined by some hyperplanes. Well, this is basically just a mathematical technical difference, let's say. Other question? Now today let's just spend some more time playing with the density matrix. Because if you remember, that was the last thing we were trying to do. We were trying to formulate statistical mechanics for quantum mechanical systems. We couldn't use phase space, mainly because we don't have the position and momentum at the same time. But we could still define what we call the rho. Now, how we defined it? Well, we can start from how can we define the expectation values of some observable, let's say G. Well, quantum mechanics tells me that this expectation value for a particular state psi I would be given by this number, this matrix element. But now let's imagine we are using ensembles. We will still stick with the ensemble theory. So what do we do in ensembles is we have our system. We have many copies of our system. So each one will have its own quantum mechanical state, well, if it's isolated, let's say. And so for each psi I, we have to take the ensemble average. We had already discussed that the ensemble average is equal to the time average, and which is equal to what we actually measure, at least in equilibrium. So we should take besides the quantum mechanical averaging, we should take the ensemble average, sum over the members of the ensemble. And divide by the number of members of the ensemble, which eventually goes to infinity. Well, we can also do it in a slightly different way. You see, if two members of the ensemble have exactly the same quantum state, they will basically contribute the same. So instead of summing over the members of the ensemble, we can sum over all psi I, but then we have to multiply this with the number of members of the ensemble. Let me just say Ni. Ni is the number of members of the ensemble that have the wave function psi I. All of their contribution is the same, so we just sum their contribution. It just gives an overall factor of Ni, weight for a given wave function. But Ni over N, at least in the limit as N, the members of the ensemble goes to 0, is nothing but Pi. Pi being the probability of the wave function psi I. Or let me, rather than calling it Pi, let me just call it, no, let me just call Pi. So this G just becomes sum over all states. The probability of that state, this is not the quantum mechanical probability, by the way. It's just ordinary probability. Multiplied by the quantum mechanical averaging. So here we basically have two kinds of averaging. One is the quantum mechanical averaging, that matrix element. The second one is the ensemble averaging, which is the classical probability averaging. Now we can write it in a slightly different form. Let's say, we have the Hamiltonian of the system, we input the resolution of identity there. Now let me change it slightly a bit. Let me just exchange the order of summation. Sum over N first. N psi I, Pi. Here I have also a summation over psi I. G. N. Or, again, let me just slightly rearrange the position of the terms. N sum over psi I, Pi, now Pi I have already written, G, N. You see, here we have an operator. Characterizing the properties of the system, of my ensemble. Let me call that operator rho. So average of G but that is again nothing but, again, this product is itself an operator. So I'm summing over N of rho times G. I'm taking the N element. But this is nothing but the trace. Now what this tells me is basically that all the information that my ensemble has is already encoded in that rho. If I know rho, I know everything about my ensemble, about my system. I know I can determine the expectation values of any quantity, which will be the quantities that I will be measuring, if I make a measurement. So I know everything. So then the question is now, what are the properties of rho? Now we looked at one of the properties, we just looked at the time derivative. Well, the time derivative of rho is the probabilities basically do not change, it's the psi i's that are changing. And just using the Schrödinger equation, we show that this is nothing but 1 over I h bar rho h. So this determines how rho changes. But in equilibrium, rho should not change. Which basically tells me that rho and h should commute. Which also tells me that I can simultaneously diagonalize rho and h. I can always write rho as rho n, sum over all states n, where h acting on n gives me the energy of the nth state multiplied by the state. These n's are the energy eigenstates of the Hamiltonian. So this will be always possible. Then what is rho n? And now we have all these different ensembles. The rho n is equal to 1 over gamma. This is the microcanonical ensemble. It's just constant independent of n. Rho n is e to the power minus beta en divided by, let's just put q. This is the canonical ensemble. And then rho n is equal to e to the power minus beta en minus mu n. This is the grand canonical ensemble. So basically all that we had done over here tells me that whatever I did in classical statistics, I can also do in quantum statistics as long as I stick with the energy basis. If I'm not in the energy basis, this will not hold anyway. Well, some other properties of this density matrix, it's more related with the quantum mechanics, let's say, but we can also use it over here. Let's calculate. So we already know what rho is. Let's look at rho squared. Well, rho squared will be pi, pj, psi I, psi j, psi I. Now I will make an assumption, which is not really necessary, but just simplifies it a lot. You see, in the definition of the density matrix, I didn't say anything about the psi I, whether they are orthogonal or not. But I will assume that they form an orthonormal basis. So rho squared is equal to J Pi Pj psi I. Well, if they're orthonormal, this is nothing but the Kronecker delta. And this is J. So rho squared is equal to sum over psi I Pi squared psi I. But Pi squares being probabilities, Pi squared is, Pi is always between 0 and 1. They can be equal to 0 and 1. So Pi squared is always less than or equal to Pi. With equality holds only if Pi is equal to 0 or 1. So rho squared, which is equal to sum over psi I of Pi squared psi I. Well, let me look at the KL element of this one. This is the KL element of that sum. Well, KL element is just PK squared Kronecker delta KL. So rho squared KL, this will be less than or equal to PK Kronecker delta KL, which is equal to rho of KL. So rho squared, let's look at the diagonal ones, KK is less than or equal to rho of KK. Well, let's see under which conditions equality holds. You see, equality holds if the probabilities are 0 or 1. Of course, since the sum of the probabilities should itself be 1, at most one of them can be 1, all the rest should be 0. So basically there is a single state describing my system. This is what's called a pure state. So there's a single wave function describing my system. Otherwise, it's a mixed state. The system cannot be really described by a single wave function. Now, this is also possible, for example, if you have entangled systems. So let's say if the wave function, let's just take the simple case that I have 2 spins, total spin is 0. If the wave function of my system is this one, let's say spin 1, spin 2, system 1, spin 1 cannot be described by a single wave function. With a probability of half its spin up with a probability half, it is done. So if you want to study only the spin 1, if you don't know anything about spin 2, the only thing you can do is use some density matrix to describe its properties. But if, so in this one, spin 1 is a mixed state. If the wave function is given by, let's say, such an expression, this is for spin 1. Here you see the spin 1 is described by this wave function, uniquely and precisely. So in this case, spin 1 is a pure state. This is also called an entangled state. This is an unentangled state. Now, we had also seen that, okay, rho, let's say in the canonical ensemble, we had said that rho is equal to e to power minus beta En and divided by e to power minus beta En. We had said that this we can also write as e to power minus beta H divided by the trace of e to power minus beta H. H being the Hamiltonian operator of my system. Now let's look at what the density matrix is for free particle. Or before the free particle, let's look at a spin in a magnetic field, which is easier. So the Hamiltonian of my system will be just minus mu b, mu being the magnetic dipole moment of this single particle, sigma dot b, single spin, let's say. Now we can choose the direction of b to be the z-axis. So this just becomes minus mu b times b times sigma z. And we can use a representation of the sigma matrices in which sigma is diagonal. So sigma z is just 1 minus 1, 0, 0. So rho operator was e to power minus beta h divided by the trace of e to power minus beta h. Now e to power minus beta h is equal to the exponential of beta mu b, b. Sigma z is 1, 0, 0, minus 1. Well, since sigma z is diagonal, our Hamiltonian is diagonal, it's easy to evaluate this exponential. This is just a 2 by 2 matrix with the diagonal entries e to power beta mu b, b, 0, 0, e to power minus beta mu b, b. Now we can write the density matrix. The trace of this one is 1 over e to power beta mu b, b plus e to power minus beta mu b, b times this 2 by 2 matrix. Now let's use it. What is the average of sigma z? This is something we had already evaluated using classical arguments. Well, we already said that this is nothing but the trace of rho times sigma z. We already know rho. Times trace of well, that trace is just 8 power beta mu bb minus 8 power minus beta mu bb divided by their sum. Now, this was something we had already obtained. So you see, in quantum statistics, I repeat, the treatment today is basically the same. We can do whatever we did in classical statistics. We can do exactly the same in quantum statistics as long as we stick to the energy basis. So that is the critical thing. We have to stick with the energy basis. Now let's look at the density matrix for a single particle, single free particle. Single free particle. Well, the Hamiltonian of my system in coordinate space. Now the Hamiltonian is minus h bar squared over 2m, the Laplacian. Now what we need to evaluate first is e to power minus beta h r1 times R2. This is what we need to evaluate first. Then if we divide this by the trace of e to power minus beta h, we obtain the matrix element of the density matrix. And the trace we can just obtain by setting R1 is equal to R2 and integrating over all possible values of R. Now the wave functions, this we can write as, let's see, we can use the energy basis, sum over n So we first need to determine what are the energy eigenfunctions and energy eigenvalues of my system. So I will be first assuming that my system is confined to a volume V. As usual in statistics, we will be assuming my system is in some volume V. So what are the corresponding eigenvalues and eigenfunctions? Well, the normalized eigenfunctions, psi n of r, which is actually nothing but Rn. These are given by e to power I k dot r divided by 2 pi to the 3 halves. And these k's can be written as kx, ky, kz. Let's just model this volume by a cube. So kx, y, or z, we can put zero boundary conditions or periodic boundary conditions. by using this plane wave solution, I basically use the periodic boundary conditions, not the fixed point boundary conditions. So if it's periodic boundary condition, then these k's can take discrete values given by 2 pi over L n x, y, or z. N x, y, or z can be 0, plus minus 1, plus minus 2, etc. So my eigenfunctions, I can parameterize them in terms of these numbers nx, ny, and z. So the sum over the states can be considered as the sum of these nx, ny, and z's, or kx, ky, kz's. Let me first put them over there. This is equal to sum over, let's say, nx, ny, and z. I will convert it to sum over kx, ky, kz shortly, times e to power minus beta. Well, the energy of this state, by the way, is h bar squared k squared over 2m, h bar squared k squared over 2m, multiplied with e to the power I k dot R2 minus R1. Now I can insert here delta nx, delta ny, delta nz. What does delta nx, delta ny, delta nz mean? Well, I'm summing over all possible values of nx, ny, and nz. And when I'm summing over nx, the nx values changes by delta nx, ny values change by delta ny, and nz values change by delta nz, which are actually 1, because I'm changing nx, ny, and nz all by 1 as I'm changing them. That's why I can insert it over there. But delta nx, delta n from this relation is nothing but delta k times L over 2 pi. That's basically how I will be converting that sum to integrals over k. So then this matrix element this is equal to sum over k, x, ky, kz of L over 2 pi cube e to power minus beta h bar squared k squared over 2m e to power I k R2 minus R1. And of course there is this delta kx, delta kz. And in the very large limit, the thermodynamic limit, you see delta n is just 1. L goes to infinity, so delta k, x, y, and z goes to 0 in the thermodynamic limit. So I'm just summing over all kx, ky, kz. They almost take continuous values. So I can just replace it by an integral. The integral of, let's say, L cubed is my volume V, D cubed K, divided by 2 pi cube. You see, if I would convert this to a momentum integral rather than K integral, I would also get the 2 pi h bar cube, which we had already used before. And then the exponent of minus beta h bar squared k squared over 2m plus I k, let me put the delta. Delta I defined as R2 minus R1. Now what I will do is I will just complete that exponential to squares. Then I will have a Gaussian integral, which the result I already know. I can evaluate the Gaussian integral. That's what I will do. So the matrix element is V over 2 pi cube d cubed k, the exponent of minus beta h bar squared over 2m k squared minus 2mi over beta h bar squared k dot delta. I didn't do anything, I just reordered the terms. Now what I will do is I will just add here mi over beta h bar squared, all of these things squared times delta squared, and then I will also subtract it. Now what this will give me is the matrix element is now V over 2 pi cube d cubed k exponential of minus beta h bar squared over 2m of k minus mi over beta h bar squared delta, all of this squared. You see, when you take the square of that thing, you get this term, you get this term, you also get this term. And there's also the last term, and the last term would just give me minus beta h bar squared over 2m times m over beta h bar squared, all of this thing squared delta squared. And this is the last term over here. Now I'm almost finished. So R2 e to power minus beta h R1. This just turns out to be V over 2 pi cube. Now the k integral is just pi over beta h bar squared over 2m to the power 3 over 2, because each Gaussian integral will give me a square root of that factor in parentheses. I have 3 Gaussian integrals because it's the 3-dimensional k integral, so that's why it's the 3 over 2. What remains is the exponential of, let's see, m minus m delta squared over twice beta h bar squared. So let me just reorganize it slightly. V over 2 pi cube 2 pi mkt over h bar squared to the power 3/2 exponential of minus mkt over 2h bar squared R2 minus R1 squared. Now let's take the trace. Let's find the density matrix. Now trace of e to power minus beta h is just d cubed R1 e to power minus beta h R1. While the exponent just becomes 1, the remaining terms is independent of R. So this is just volume times V over 2 pi cube. Now let me rewrite it slightly differently. V over 2 pi cube 2 pi mkt over h bar squared to the power 3/2 times the integral of d cubed R1 of 1. because everything else in that matrix element I already took it out of the integral. Now R2, row of R1. Now we can write down the matrix element of the density matrix finally. This is equal to R2 e to power minus beta h R1 divided by the trace of e to power minus beta h. You see, the trace of e to the power minus beta h is nothing but this term multiplied by v. So when I divide it, this matrix element is just 1 over v times exponential of minus mkt over twice h bar squared R2 minus R1 squared. Now, the diagonal entries of rho, let's look at this one in general. This was pi and psi I n, which is pi absolute value of n psi I squared. You see that n psi I absolute squared is nothing but the probability that given a system in the state psi I can be observed in the state n. So we have the quantum mechanical probabilities averaged over the ensemble. That is nothing but the probability, ensemble probability of observing the state n. Well, let's just apply rho and n in a sense. In a pure ensemble, in a pure state, let's say, it's nothing but the quantum mechanical probability. In a mixed state, it's the averaged probability, let's say. Now we can apply it over here. This was what we had obtained for the free particle. This is the probability that my particle is at the point R. Now you see this is nothing but 1 over v. But as expected, because there's no potential, there's no special point in my volume. So every point is equally probable. As a probability density in this case, because it's a continuous position. Well, everything is kind of just turns out to be consistent, let's say. Now things get a bit more interesting when we have more than one particles. But I think I would rather stop here for today. And let's do one more thing here. Calculate the average energy, expectation value of the energy of the free particle. And then for identical particles, we can just leave it for tomorrow. Artan can also be here. So the average of the Hamiltonian for this system. Well, this is nothing but the trace of rho times h. This is nothing but the integral of d cubed r, or rho h r. Well, this is equal to d cubed r, d cubed r prime, let me say r1 and r2, r1 rho r2 r2 h r. Or let me just take a slightly different route. Trace of h rho. In the trace I can just exchange the two operators. This is equal to trace of the integral d cubed r, r1 or r2, r1 of r1 h rho r2 evaluated at r2 is equal to r1. This is equal to, now I know what the coordinate representation of my Hamiltonian is. This is equal to d cubed r1 minus h bar squared over 2m Laplacian with respect to r1 of r1 rho r2. Now, I already know what that matrix element is. D cubed r1 minus h bar squared over 2m Laplacian with respect to r1 of 1 over v times e to the power minus r1 minus r2 squared divided by lambda squared. Now I defined lambda squared to be all this thing inverse. Now let's evaluate that Laplacian. Of exponential of minus r1 minus r2 squared over lambda squared. Well, the easiest will be to use the Cartesian coordinates. So this is equal to xi, the xi being the xyz of the r1 of the exponential of minus r1 minus r2 squared over lambda squared, which is minus twice xi minus let me say r2i divided by lambda squared e to the power minus r1 minus r2 squared over lambda squared. When I take the second derivative with respect to xi, there are two terms I have to differentiate. First, the overall factor xi minus r2i, then the exponential. But keep in mind that I will eventually set r1 is equal to r2. If I don't differentiate the first term, when I set r1 is equal to r2, that is xi is equal to r2i, that term will just give me 0. So the only contributing term eventually will be the first, when I take the derivative of the first factor. So this will be equal to minus 2 times 3 over lambda squared times e to the power minus r1 minus r2 squared over lambda squared plus terms that vanish. When r1 is equal to r2. So now I'm almost done. This is what I'm trying to evaluate. Well, this is equal to minus h bar squared over 2m times t cubed 1 over v times t cubed r1 times minus 6 over lambda squared times 1. Because now I set r1 is equal to r2. Well, the volume integral just gives me, this minus will cancel this one. This integral just gives me v, which cancels this v over there, so I have 3 h bar squared over m lambda squared. Now, 1 over lambda squared is just this factor over here. So m's cancel, h bar squares cancel, and we are left with 3 over 2 kT, which is the result that we had already known. For a single particle, at least, the average energy in 3 dimensions, a non-relativistic particle just turns out to be 3 over 2 kT. So again, everything just turns out to be consistent with what we had done before. Now, of course, things will become more interesting when we start the identical particles. So, because there were already we had some discussion about the identical particles. Now here, at least in the quantum mechanical systems where the quantum mechanical effects will be important, the property of being identical will be important. Questions? Okay, so let me give a break here, and then tomorrow we will continue.